from the earlier lecture with reference to shape memory alloy, fundamentals of shape memory alloy. So, you might have observed that one of the tedious process in applying this shape memory alloy for different functional applications is the training of shape memory alloy. Okay, because as far as this training cycle is concerned, and most of the cases, like since it works on the principle of this austenite phase and martensite phase, we may need to prepare a die and we may need to immerse it inside a we may need to put it in a muffle furnace, and then we have to immediately quench it in either in a liquid nitrogen or in a cold water conditions. And one more point is something like we may need to repeat this cycle close around 50 to 60 times to get a higher like recovery. So, recovery percentage. So, this is a kind of when we try to energy efficiency perspective point of view, this is a kind of a waste of an energy. And the second thing is it's highly a tedious process. So, in order to avoid this, so there is we can integrate this SMA with a kind of a material. So, that is what we have been discussing in terms of bimorph. Okay. So, like in the earlier composite case also, what we have done is we have programmed the material and we integrated the material with a composite structure. So, that what happens is this composite structure will work along with the shape memory alloy to get an appropriate actuation or the appropriate characteristics. Okay. Now, as far as this realization of shape memory alloy is concerned, like we can introduce to this new concept called SMA bimorph. So, as far as in this SMA bimorph, so what we can do is like we have a shape memory alloy and Kapton polyamide. The shape memory alloy is integrated with Kapton polyamide, so that the shape memory alloy takes care of the actuation, and then for the return stroke this Kapton polyamide will participate with shape memory alloy for the return stroke. So, that is what is the thought process. Now, with this as an idea, so we had developed a small Stewart platform for micro robotic applications, which is used for beam steering. So, let us see this particular case study. So, we can discuss about the different processing steps involved, the different evolution involved in this particular process in detail. Now, the key motivation of this particular case study is like in most of the flexible mirrors, like for example, if we have a mirror of a large area, normally these mirrors are where we are looking for some kind of dynamic actuation. So, these mirrors are integrated with a kind of a actuator. In most of the cases, it might be a kind of a hydraulic actuator. In some cases, it might be a kind of a mechanical, it might be a kind of a linear electrical actuators. In certain cases, it might be a kind of a piezoelectric actuator based on the response normally it is considered. So, the element of reflectivity is different, the actuator is different, the actuation characteristics will take care of the overall reflection behavior. Now, in this particular case, what we thought is, so if we need to make the system simple, so why don't we prepare a deformable mirror which can be actuated, which has its own capability towards actuation. That is, if we can go for a high reflective shape memory alloy thin film, so that this thin film has a capability to get actuated appropriately. So, one of the key concept what we thought is, so we will make a flexible and a customized structure which can be achieved, and then we can develop a mirror with a kind of a tunable reflectivity, so that these tunable reflectivity can be efficiently deployed for the deflection of the or for manipulating the beam based on the requirement. Third important point is with reference to the robust structure compared to the available electrostatic and piezoelectric mirrors. So, it can act as a kind of a alternative to the electrostatic and piezoelectric mirrors, because in the case of electrostatic or piezoelectric mirrors, of course, it has a higher order frequency, but however, with respect to like linkages perspective point of view, so what we may need to do is we may need to connect an actuator on the mirror. So what is happening is these become two different elements, and these two different elements gets actuated to get the required motion. Okay. Now if we can design a system where a bimorph itself can act as a mirror, and it can be integrated with an additional bimorph actuator to take care of the intricate design, so that the overall load of this Stewart platform can be considerably reduced, and it should have a higher flexibility. So one of the key objective, or one of the key like outcome of this particular project is to develop a customized actuator. Then second, an actuator with a low power consumption, and like the actuator which designed is on a micron order, however it has a capability to go for a macro range motion. So that is what is the thought process. Now let me just introduce you to this shape memory alloy bimorph. So we have already seen the shape memory alloys has a high work density and a high surface area to volume ratio. So it has a capability towards high frequency and cooling rate. So what we are trying to do is, this is a kind of a SMA deposition chamber. So in this SMA deposition chamber, there is a tungsten boat is there. So this is a kind of a thermal deposition unit. So this thermal deposition unit can be used to deposit shape memory alloy structure. Now one of the important point which you may need to consider is our feed material which we are planning to use. So based on the composition, we get powders. Like for example, if I want to make a quaternary alloy, or if I want to make a ternary alloy, so I can take Ni, Ti, Cu, etc., and I can make it in the form of a pellet in a arc melting chamber. So in an arc melting chamber, we try to make a pellet, and this pellets can be integrated with the tungsten board, and then we try to supply a kind of an electrical biasing through this. Through this electrical biasing, the material gets melted and it gets deposited on a substrate holder. So the entire things will happen in a vacuum environment. Since this system is called as a flash system, that is instantaneously the power is applied to the tungsten board, so that there is a kind of a rapid heating of the material and the rapid evaporation of the material on the surface. Now if you try to see the overall mechanism which is happening in this, so this is the kind of a Kapton sheet which is used. So this Kapton sheet is initially in a curled phase. So when we try to put it on a substrate holder, we try to straighten it. So already a shape is preset in this Kapton sheet, and now using a substrate holder, then in this preset condition, so we are trying to straighten it and then go for a thermal deposition. So this thermal deposition, the thickness of the material will be in the order of less than 1 micron, close to around 0.25 to 0.5 micron, where the deposition happens, so that it takes the curl shape, that is a Kapton sheet. After deposition it gets curled, and when we try to put it in a hot plate, so it tries to get biased. So as far as in this bimorph actuation is concerned, so you can see over here, this is on a hot plate. When we try to put it on a hot plate, it becomes straight. When it is taken in an open environment, it takes a curve structure. That is the switching between the actuation domain. Now in order to preset this particular or in order to set this particular shape setting on the SMA bimorph, so two different techniques has been followed. So one technique is something like, we take a Kapton polyamide and we strain it using a fixture, and then the straining is done in a tensile testing machine. In that tensile testing machine, further it is being placed within the two pulley arrangement in this particular fashion, and this pulley arrangement is in such a way that the shape setting will be continuously deployed during the deposition. So what happens is, this pulley will be always in a kind of a strained condition. So this is what we call it as a programming the shape memory alloy for our requirement. So how much is the frequency we require, how much is the displacement we require, appropriately straining is deployed over here. Now we have a kind of board kind of arrangement. So in this board kind of arrangement, so already we have kept the pellet which has been manufactured, or like which is of the requirement to make an appropriate composition. Now a kind of an electrical biasing is applied on it. So these electrical biasings are like capable enough in such a way that there is going to be a kind of a evaporation which persists, and this deposition is going to be a kind of a continuous deposition. So what happens is, since you have a pulley arrangement, these pulleys are connected with the motor and the motor to the idler pulley, and when the rotation happens, there is going to be a continuous deposition of the material. So this continuous deposition will result in the kind of a deposition belt over here. So overall deposition is in the form of a sample size that is close to around 2 cm to 50 cm belt. The deposition bar in the range of 2 into 10 power minus 5 millibar. The deposition current which is used is close to around 380 amps, and then appropriately only 1 gram is used. So based on the weight, appropriately we can have a kind of a varying thickness what we are going for. Now this is the case which in the earlier case we have used a flash evaporation. So wherever we want to make a bimorph, so we go for this flash evaporation. That is, wherever we want to go for a low density film, that is, this film will not be highly reflective, however it has a better actuation. So like for these better actuation property, such kind of thermal evaporations are deployed. However, wherever we want to go for a high density film, then we can deploy a kind of a E-beam based system. So in this E-beam based system, so what we try to do is, so we try to put the source over there, and then using an E-beam, the source is getting evaporated, and then there is a kind of a continuous evaporation which happens, and because of this continuous evaporation, there is going to be a thickness in the overall structure. So this thickness will result in a so you get a kind of a, in per unit area there will be a more amount of high density structures which will be fabricated over here. So because of this high density structures, so you get a high density film which exists. So in this high density film, so we have a kind so like these are the different process parameters which are employed. Since an E-beam is used, so these E-beams are capable enough in such a way that quite a good amount of energy is getting imparted on the material, and this material will start depositing, and finally, like as shown before, like here also we have a kind of Kapton polyamide. These Kapton polyamides are strained appropriately so that there is going to be a continuous deposition which exhibits over here. So because of this continuous deposition, so you can have a thicker high density film which is almost equivalent to a kind of a mirror can be established over here. So this is a kind of a customized system. It's a kind of a PVD based system which is being deployed. In fact, regarding PVD, so we had discussed a lot in the microfabrication. Now let us see the characterization of this electrical actuation. So as far as in this electrical actuation process, like if you closely observe the cycle, so this is like initially it is in the state, and this is the representation of a tip displacement. So what happens is, as the tip increases, so appropriately the displacement also increases with reference to time t, and then there is a decrease in the tip displacement. So this cycle is called as a repeatability cycle. That is, this cycle we can call it as a kind of a like reliability cycle. So in order to get this cycle, so normally we have a kind of setup which we will be showing it during the demonstration also. So in order to get this repeatability cycle, so what we do is, so we keep the SMA bimorph, and then the overall repeatability of the structure can be monitored using a laser displacement sensor. So in this laser displacement sensor, the light is made to interact on the tip, and when there is a continuous actuation happens, there is a reflection which persists, and from the reflection we can estimate the overall cycle. So the voltage is close to around the voltage which is supplied to is close to around 25 to 25 volts, and 0.25 amps is the overall input to this particular system, and the frequency which comes close to around 0.25 hertz. And as far as this displacement is concerned, we can have a control over the displacement. Roughly the displacement is in the order of micrometer. So basically from 60 micrometer to 75 micrometer can be easily established using this particular SMA bimorph. However, the overall actuation characteristics or the frequency characteristics can be efficiently catered by changing the thickness. So by appropriately changing the thickness and appropriately changing the strain percentage of the kept on polyimide, so we can have a higher order frequency what we are looking for. Now how? So this is a kind of a initial trials. So this is a kind of an SMA bimorph mirror which has been fabricated using this technique, and then a kind of a since it is used for a beam steering, so the incident beam is made to incident on the beam and the reflected beam is collected on the screen. So this is a kind of a power source which is being employed for the bimorph. So basically, since the actuator has a capability to actuate at a high frequency, so we can also deploy a programmable power supply. So this programmable power supply can be integrated with the bimorph for a higher order frequency. So you could observe in this particular video. So this is a kind of a laser which is being interacting with the bimorph, and this bimorph is reflecting. So the bimorph is over here. The connection for the bimorph is taken through these leads, and from the reflection you could see the overall sweeping of the mirror which happens. So the mirror gets swept and appropriately it is used for reflecting the beam. Now one of the microfabrication which was followed over here is like we have induced a kind of a roughness is induced on this polyimide substrate in order to improve the efficiency. Like you may ask a question like whenever such kind of bimorphs are prepared, there is a question of adhesion, because like these are completely two materials which are being bonded using a kind of a coating system, using a coating technology, and then when we try to actuate it, so there is a chance that these film may get peel off. In fact, when we are discussing about this substrate selection, so I had discussed about two different types of substrate selection. One is substrate integrated with the SMA, and another thing where both substrate and the SMA, both substrate and the thin film will work together and it will result in a kind of actuation. And the other technique is something like the substrate and the SMA, where the SMA can be peeled off and the substrate can be used separately. Now in this particular case, so in order to improve the, because here we are trying to work on the frequency. So if you are trying to use it for a mirror application, of course one important aspect is like we may need to run it at a higher order frequency. So at these higher order frequency, at any cost there should not be any peel off of the material. That is one important aspect. So there are different techniques which are deployed to improve the adhesion. So one property can be something like we can go for a plasma treatment of this polyimide so that the adherence of the polyimide will be improved, and appropriately when we go for a coating, so appropriately we can get a characteristics. Another one method is something like we can go for a kind of a pulsed laser crystallization. So using a pulsed laser crystallization, what we can do is we can modify the surface based on the requirement, and then we try to go for a coating, and then once we go for a coating, what happens is these modified layers will act as a kind of a anchoring medium. So in this anchoring medium, so once you go for a coat, so these anchoring medium will have a more amount of addition. That is like we are trying to manipulate the surface to volume ratio appropriately so that you can have more amount of addition. So with more amount of addition, so appropriately you can have a kind of a larger life cycle what we are looking for. So this is the overall steps which are being followed. This is a kind of a pristine polyimide substrate which is integrated with the laser annealing, and then with the laser annealing the deposition is performed using a thermal evaporation, and with the thermal evaporation an NATA SMA bimorph and the as fabricated bimorph and the actuated bimorph are integrated over here. Now like in this particular case, so we have a different parameters which are being established over here. So it's a kind of a surface treatment which is being done to improve the capability. Now this is the system which has been fabricated. So this is a kind of micro-position based Stewart platform which has been fabricated. So in this micro-position based Stewart platform, there is a SMA bimorph mirror. So the mirror is in the form, and then there is an SMA bimorph based actuator which is integrated along with the mirror, and these are individually connected to a relay kind of system in order to monitor the position and the orientation of these SMA bimorph mirror. So appropriately, there are certain amount of arco markers are being placed over here. So these arco markers act as a reference in such a way that when we try to actuate it, so appropriately it moves. So in this particular construction, if you see, so there is a kind of a micro-positioning stage with the arco mirror and a mirror, and then there is a camera which is being placed and a motion controller and a computer. So this camera is used for observing the overall mirror, and then there is a micro motion controller which is available. So through this micro motion controller, we can see the behavior. So like we can have a kind of a deflection in this plane. So let us consider this as a z-axis and this as a x-axis, and then the deviation in the x-axis between the z-axis is mentioned as theta axis. So this theta axis is like it is on a micron level for shifting the beam. Okay, so like if you see the overall response of this is a kind of a micron inclination which has been observed. So in this micron inclination, the overall system is designed in such a way that the maximum inclination of the mirror achieved was close to around 28.76 degrees, and about x-axis it is around 8.46, and about y-axis it is around 1.19 degrees, and about the 1.19 degrees of z-axis, 8.46 of y-axis, 27.76 along x-axis. So appropriately, the Stewart platform will create a work volume over the position, and the mirror inclination with a single bimorph and two bimorph actuation for 8-volt input, and it has a kind of 0.25 Hertz cycle which is being kept over here. So now in this particular case, so we have about the angle about the z-axis, angle about y-axis, and angle about the x-axis which is being represented in this particular domain. Now here you could see this is the overall construction, in fact, which is deployed for actual conditions. So in this deployment, what we are trying to do is a mirror is placed over the Stewart platform. So the mirror is a kind of a is slightly a kind of a rigid mirror which is being placed, and so since we have a capability, since it is possible to fabricate a mirror with SMA bimorph, which is a kind of a static bimorph, and then for an actuation perspective point of view, these mirrors are integrated in this particular fashion so that the actuations can be appropriately controlled, which has a direct relevance towards the degrees of orientation along the x, y and z plane. Okay, and this is the incident laser beam, and a camera is used to capture the overall orientation of this particular beam and its appropriate characteristics. So in that aspect, if we see, so this orientation, it has three different types of orientation. So one is along the theta x orientation, and the other one is along the theta z orientation. So as far as theta x orientation is concerned, so a degree of around 1.01 degrees plus or minus 0.18 degrees where could be achieved, and with reference to z direction 0.42 with 0.05 could be achieved. So the direction has a direct relevance towards the degree, and appropriately a laser beam is being diverted over here. Now let us see the overall fabrication procedures which are being involved in this. Now in the earlier case, a kind of a Stewart parallel mechanism has been fabricated. Now we will see a mechanism where an optical shutter, an optomechatronic shutter has been developed, so which has a capability to open and close in such a way that it can restrict the light which is entering into this optical shutter. So this is a closer view of the laser beam steering. So if you closely observe, the overall deviation is well controlled, so there is no undulation in the system, and then like all the theta x and theta z are well recorded, and then the overall micro manipulation is in the order of close to around less than 100 micron is the observation which is here. Now let us take one of the sub case study in this. So in this case study, what we are trying to do is, so we are trying to fabricate, so we are planning to fabricate a kind of a SMA based like optical shutter. So the main application of this optical shutter is, so it opens and closes, and it restricts the overall interaction of the light inside a particular system. So in fact the optical shutter looks something like this. So in order to fabricate this, again, so we are fabricating the SMA bimorph. So in this SMA bimorph configuration, so what we are trying to do is like through a vacuum arc melting, the concerned pellets are made, and then these pellets are used as a source material for the thin film deposition. So in this thin film deposition, there is a graphite crucible, and then the source material is applied, and since it is used for optomechatronic application as discussed earlier, so we may need to have a high density film. So the high density, in order to get a high density film, a E-beam evaporation technique is deployed. Now in this E-beam evaporation technique, so we get a strip of SMA bimorph. Now we may need to dice this SMA bimorph based on the requirement. Since we are looking for a kind of a micro level actuation, so it is easy to fabricate such kind of micro level process using a kind of a laser. So this is a kind of a fiber laser which is used. So during the overall process, these kind of SMA bimorph are strained, and a laser beam is used to interact with the bimorph, and then appropriately it is being cut. So the different laser parameters are used, and this is a kind of a SMA bimorph which is being fabricated. So you can see a closer demonstration over here, closer video over here. This is a SMA bimorph in which the concerned features are cut using a laser. So this acts as a petal. So these petals are fabricated using a laser. So based on the type of configuration, different molds are used for fabricating such kind of structure. This is a kind of mold which are being deployed for the large area process. This is a kind of mold which is being deployed for a kind of a circular process. So these are some kind of various configurations which are being deployed. So one set of configuration is in the form of a triangular form. So one set of configuration is in the form of a kind of a like a lotus petal kind of form, and then the connections are established in such a way that like the overall leads are taken in these particular dimensions, and the leads or contacts are established in such a way that instantaneous opening and closing takes place. However, there is a possibility to have a different configuration in this. So in this particular configuration, what we can do is individually these systems can be connected, so that there is a kind of an individual actuation which happens. Like for example, you can have a multiple relay structures. So in these multiple relay structures, so there is a kind of opening and closing of these relays. So appropriate opening and closing of these relays, there will be an open and closure of these SMA bimorph, and appropriately actuation happens. So in this particular case, if you keenly observe, like in order to have a control over the multiple micro actuations, we can have an individual relay control, and these relay controls will give a signal for appropriate actuation. So this is an overview. Like in fact, this talks about a kind of a micro robotic platform which is developed for a kind of optomechatronic applications, and what are the stages involved in developing such kind of micro robotic platform for especially the different stages involved in micro fabrication, and then what are the different how the reliability and life cycle behavior of these structures are deployed, how close is the features are being generated. So this is just to give you an overview and feel about how micro robotic structures can be fabricated. Okay, now we will discuss about the overall limitations of these particular shape memory alloy structures. In fact, we have discussed in detail starting from the overall configurations, the types and the reliability about the different devices, etc. So one of the major limitations of shape memory alloys are it has a high cost of production, especially with reference to an internal perspective point of view. That is the reason the raw material cost is quite high. Second thing, it has a slight complexity in machining of SMA. So, which I had mentioned earlier, like for example, if you take a small rod or a small sheet, and if I want to do a kind of a drilling in this particular process, so whenever I try to impart a heat on this particular material, this particular material will try to get deformed and regain its shape. Okay, so it is very difficult to hold this material for a longer period, which is one of the key challenges when we try to use such kind of materials which are like highly sensitive to heat. However, it has its own complexity, and then it has its own limitation towards transformation of temperatures, and it has a complexity in controlling the SMA based systems. So strategically these materials are well represented in different defense and space related applications owing to its capability with reference to owing to its capability for actuator as smart actuator, smart sensor, smart microsystems, smart micro robotics, etc. However, a future perspective point of view, like there is a possibility of exploring a cheaper alloy, and then currently 3D printing has taken up a shape in fabricating such kind of shape memory alloy structures. However, with 3D printing process, there is a chance that it is very difficult to maintain the functionality of these particular shape memory alloys. So still 3D printed shape memory alloy structures are not commercially available, which may be a kind of a future prospective direction where 3D printed structures may come up and it may take up a shape. And then like these kind of 3D printed structures can be integrated with material for appropriate integrations, and then more amount of applications can be taken up. Most important challenge with reference to field perspective point of view is a training part. If so, currently the training are overcome through this either through this bimorph or through a kind of a strainability, etc. But however, if kind of a simple training technique can be followed, so that this will open up a new domain for usage of these kind of actuators for different application. And second important point with respect to shape memory alloy is concerned, like either it is on a micro level or it is on a macro level, it almost behaves in the same fashion. Okay.